In this video, I'll be going through a couple of problems from 6.4 exercise 2. We're going to skip over exercise 1, just simply involving more translating, and head directly to exercise 2. So let's begin by making note of the directions. The directions here, exercise 2, 6.4, read as follows. Determine whether the following symbolized arguments are valid or invalid by constructing a truth table for each. So some more vocab. However, it's vocab that we've already encountered. Valid and invalid are terms straight out of chapter number 1. So hopefully you're already familiar with these terms. But if not, there'll be a friendly reminder in solving these problems. Obviously here the problems in exercise 2 look a little bit different than we're used to. The problems in exercise 2 are written out in standard argument format, a series of premises. Then we see that long horizontal line separating out the premises from the conclusion. So to begin the setup in exercise 2, we first want to take those problems written out vertically in standard argument format, and we want to write them out horizontally. So I'll just jump in here to problem number 1. Only way to learn logic is to solve problems. The first premise of problem number 1 is K, horseshoe, not K. Then we see the horizontal line separating out the conclusion. Rather than using a horizontal line, since we're writing it out horizontally, I'll use a double slash. So premise 1, double slash, we're ready for the conclusion, and the conclusion is not K, not K. So to begin, write the problems out vertically, using a double slash to separate out premises from the conclusion, and a single slash to separate out the premises. There was only one premise here, so we didn't need to utilize a single slash. But if you have multiple premises, separate out those premises with a single slash, and then separate out the conclusion with a double slash. So that's how we write it out horizontally as opposed to vertically. Now the second step is the same step that we've been using for the vast majority of chapter 6. Count up the number of unique variables, plug it into the formula, L equals 2 to the power of n. So in this case, one unique variable, we've just got k's. 2 to the power of 1, of course, is 2. So our truth table will be pretty short, just consists of 2 lines. Take that number 2 divided by 2, and 2 divided by 2, of course, is 1. So starting on the far left, once again, we start with put a single t followed by a single f, and that defines force the k. Every time k appears, define it the exact same way. The next appearance of k is negated, so I'm going to take that little shortcut. Instead of starting with t as I normally would, I'll reverse it and start with f, then going to t, and there I'll take care of the tilde right away. Now on to the conclusion. We need to define this appearance of k as well. The same will hold for the second appearance as compared to the third. This third appearance also negated, so I'll reverse the pattern starting with f instead of t. And that here gives us the truth table. The next step is to solve for each of the premises, in this case there's just one, as well as the conclusion individually. So I'll start with the premise. We've already taken care of the tilde, so we just need to now solve for the main logical operator. T horseshoe f, special case false. F horseshoe t is true. And now the conclusion. The conclusion, actually in the setup of the problem, we've already taken care of immediately. We're already done with it. So we've solved for our truth table, and we now just need to apply the vocabulary. Is it valid or invalid? Let me go ahead and circle the column underneath the main logical operator of both the premise and the conclusion. So is it valid or invalid? If the statements, or if the argument that is, if the argument were invalid, there would be at least one line where each of the premises, in this case there's just one, but each of the premises turn out to be true and the conclusion false. If it is possible for the premises to be true and the conclusion to be false, then that's the very definition of invalid. If there's a case, if there's a single line where every single premise, no matter how many there should be, if there's a case where every single premise turns out to be true on some line and the conclusion turns out to be false, then it's invalid. So that's the special case that we're looking for. If there isn't any such case where all the premises are true and the conclusion is false, then it is valid. So let's examine this particular problem. Do we see a line where all the premises, and in this case again there's just one, where the premise is true and the conclusion false? Well, the first line of the premise is false, so no need to go any deeper. In the second line, the premise is in fact true, but the conclusion also turns out to be true. Therefore, it's valid. And that really is all there is to it. Just to make sure that you've got it down, let's solve one more problem together. Let me skip ahead a little here to problem number 4. So I'll begin by writing it out horizontally. The first premise is not, parentheses, G and M, close parentheses, and that's the first premise. On to premise 2, I'll separate it out with a single slash. The second premise is M or not G, and we're now ready for the conclusion, so I'll separate that out with a double slash. The conclusion is just simply not G. So count up the number of unique variables, 2, plug that into our formula, and there are 4 lines in our truth table. Start on the far left-hand side, take that number 4, divide by 2, and we start with 2 consecutive T's, followed by 2 consecutive F's. So that now defines for us G. Every time G appears, repeat that exact same process. The second appearance of G is negated, so I'll take the shortcut, reverse that pattern, starting with the F's, and then going on to the T's. And the same holds for the third appearance of G. It too is negated, so once again I'll reverse the process, thereby taking care of the tilde just in the setup of the problem. Now we just need to define the M. In defining G, we had started with 2 consecutive T's, so we'll take that number 2 and divide by 2. 2 divided by 2 is 1, so to define M we start with but a single T followed by a single F, and repeat that process until you've filled up all 4 lines. Every time M appears, define it the exact same way. One more time to go, and this gives us our truth table. So from here, really, we have 3 separate problems to solve. Solve premise 1, solve premise 2, and then the conclusion, and then we'll apply the vocabulary. So I'll start with the first premise, main operator is the tilde, so we need to take care of the dot first. T and T is true, T and F false, F and T false, F and F false. Now the tilde. T becomes false, F becomes true, F becomes true, and F still true. Circle the column underneath the main operator and on to premise 2. We've already taken care of the tilde, so that just leaves us with a wedge. T or F, that's true. F or S, special case false. T or T true. F or T true. Circle the column underneath the main operator, and we're now done with the second premise, leaving us just with the conclusion. We've already solved that, so I'll go ahead and circle the column there. Now we need to determine if it's valid or invalid. And again, we're just looking for that special case. Is there a single line where both of the premises, in this case, where both of the premises turn out to be true and the conclusion false? That doesn't happen in the first line, doesn't happen in the second line, doesn't happen in the third, doesn't happen in the fourth. So again, since there's not a line that looks like that, both premises true and the conclusion false, since there isn't any such line, it is valid.